Can you see my screen online?
Yes, sir.
Yeah. And you can hear me clearly, right? We reduced the volume a little bit because there was an echo. You can hear me, right?
Yes, sir. We can. Yes, sir.
Okay. So what we are going to do today is to first quickly finish the syllabus. It's about HTTP. And as I said last time, we are doing it mostly for completeness, but I don't really like teaching it. You know, it's a fun protocol to implement. In other years, we actually give it as part of HTTP to be implemented as part of your network lab. But in terms of teaching it, it's just some more details and so on. But still, you know, it gives you an idea that everything is not like the FTP protocol that you did. So it's an application layer protocol. And you know what is the definition of application layer protocol? Uses the services of transport layer protocols to enable different application specific services. The standard definition has a huge number of application layer protocols. It's hardly, you know some of them: FTP, Telnet, HTTP, POP IMAP, SMTP for mails. So, you know what is POP IMAP and SMTP? They are all three are for mails, right? But what's the difference? Can I just use any one of them for mail?
Sir, SMTP is for sending mail. POP is for retrieving.
Exactly. POP and IMAP is basically two protocols for retrieving mail from the mail server. SMTP is to actually send and receive mails between mail servers, basically. So POP and IMAP is more, SMTP, rather mail clients like your, Outlook, whatever, to actually connect to the server and download mails and so on. Then you have remote desktop protocol, real-time protocol, n number of protocols basically. So we'll just cover basics of HTTP just as an example. It's hypertext transfer protocol. You all know that. It's a TCP-based protocol. So there was originally HTTP 0.9, then there was a 1.0. Both of them are obsolete right now. Nobody uses them. So 1.1 came, I think, in 1997, I think, most likely. So that has kind of stayed on. It has almost everything, supported by all websites. 2.0 is also widely used, standardized in 2015, and roughly around 50% of the websites support it. And 3.0 is also there, but not standardized yet, basically. So we'll just cover some basics of HTTP 1.1 just to give you an idea about the protocols. So it's a protocol for accessing resources or objects on the internet. So you need names for them. And the standard way to name them is URLs. I think most of you are aware of this already. Only interesting thing may be that, again, I think most of you are aware of this, that it's actually three parts, and this first part basically specifies the protocol that you should use to access it. So it doesn't need to be HTTP. The URL can be used to kind of specify anything that is accessible over the internet. Okay. So a browser sees a protocol in a document called FTP colon this, it can invoke the FTP protocol to download that and so on. Okay. And it can also specify query strings, parameters to pass. For example, the way you do Google search. If you ever just press Google search and see what is the URL that goes, you will see a question mark, query string, and so on and so forth. Client server, obviously, opens a TCP connection to server, obvious. Default port is 80. And if you have noticed, nowadays, almost everything is HTTPS, which is basically HTTP along with some security. So I'll talk a little bit about it at the end. So default port for HTTPS is 443. So broadly, the basic HTTP operation is client send request, server send response, obvious, just like any other client server. And the requests consist of what we call methods along with the URLs on which we want to apply the method and some parameters. Okay. And the server will send a response. The response will always have a status code, successful or not, or otherwise indicating. So these are those 404 not found, 403 forbidden, those 404, 403, all those things that you normally get. And this response may have content depending on the request method. Some responses will have content, some responses will not have content. So we'll see all that. So presentation of the content is not part of the protocol. Okay, any content can be downloaded. You can get HTML, PDF, text, whatever. So how do you present it, interpret it, and so on, is not part of HTTP. So that we are not going to cover. What is interesting is HTTP1 is a text-based protocol. Okay. So if you do a plain HTTP, nothing encrypted, nothing, you should be able to see actually in text what goes on and goes out. Similar to SMTP, for example. Okay, SMTP POP, basic SMTP, they are all text-based protocols basically. Unlike this FTP and all that you saw, basically, which are something little bit different. And the other thing is HTTP is stateless, mostly. A slight, okay, let's not get into that. It's stateless. Okay, so server just gets the request, gives a response. That's it. Doesn't need to do anything else. Oh, I have not. So what are the methods that you have? You have a get. So get and oops, sorry. Get, put is probably the two of the put and post. These three are the most common methods that you will see. So get will just get the content of a resource. Head will just return the header of the resource. So sometimes you just want to see the validity of the URL, basically the document is there or not, but without getting the content or so. Or just want to collect kind of the type of the content, etc. But you're not yet interested in the content itself. Post and put is what is a simpler thing. Post is replace the context. It's just like a write, basically. And the post is kind of treat the document as a script and send some data to it. Now, depending on what that resource is, it will do different things with the data. For example, if I see CGI script or something, JavaScript or something, it's actually going to run that thing with the data as parameters and give you back the response and so on. Okay. Other than that, it may actually just overwrite the data also. Delete is delete the resource. Trace is just, the server will just send you back your own request minus some headers. This is just to see the server is working, it's understanding your request properly or not and so on. And options and connect. Connect is basically a special thing for connecting through proxies. So when you say connect to somebody, that somebody is a proxy server, it knows I am not the final thing. It's actually going to do a actual method connect to the actual server and so on. Okay, but only for going through proxies and so on. And options are, you have several options to allow a client to know what methods headers can be used with the resource and so on. Okay, again, I don't expect you to remember all these things, but at least know if I ask you, like, give you some simple solution, even though I think online there is very little chance of getting questions like that. Name 4 methods in HTTP. Okay, you give these things offline so that everybody gets some marks. Basically, you just want to see whether they know something. Okay, you don't get 3 because then 3 is get, post, put. Whether you remember at least one more and so on. We have our tricks also. Okay, so here is your broad HTTP message format. You will have a request or a response line which will contain the methods and so on. There is a bunch of header fields, one in each line, again all texts. You'll have a blank line and then there's an entity which is the actual content. If it is there, it will be there. So let's just look at examples rather than going through this. So online people, you can hear me properly? No problems?
Yes, sir.
Okay. So the headers, even though they need not come in a specific order, we divide into 4 parts. The general header, which are basically headers that are, this is a kind of general, whether it's a request or a response. Both can have this. Request headers, which can only be in the request. Response headers, which can only be in the response. And entity headers, which correspond to something to do with the entity. So again, I will show you a lot of header fields. There is no compulsion to remember all of them, but you should remember that there are these 4 different types of header fields and so on. And I'll show you some examples also. So cache control, for example, specifies some information about caching. It can say, don't cache this document. So when the server sends a response back to you, it can say cache control : no cache, which means the browser should not cache it. Okay. Connection, we'll see again an example I'll show you. Date is date. Okay. And mime and upgrade is not very important for you right now. Request headers, again, It says when I am sending a request, I'm saying what is the kind of document I'm willing to accept. Okay. So for example, I can say that I'm only going to accept US English. So that will be, I can specify accept language. Okay. So there is a set of very fixed hard-coded, keyword sort of things out there, and you specify them saying, I'm going to accept language this. And this can be very, this is quite powerful. I'm just going to kind of give you very basics. So you can specify that I will prefer a US English, but if it is not there, then my next choice is, British English. If it is not there, give me anything. So you can do things like this also. Okay. So accept language and accept are the easier to understand. Accept is the medium format. Can I accept anything? Or do I want only text files? Do I want only PDF files, only HTML files, and so on. Okay. And these other things are basically more with caching and all, if modified scenes. So I say, give it to me only if it is modified beyond this step. Because otherwise, I already have it in cache, basically. Okay. You can do many things, if match, if non-match, okay, if unmodified scenes, okay. And user agent is just information to the other side, basically says what kind of browser you are using and so on. I'll show you examples of this. Response, much less fields. There are some more header fields is not there. This is cut and paste from Farozan's book. Okay. Luckily, it's showing actually a better, brownish color in there. Okay. In my computer, it shows a complete pink color, basically. So it shows the age of the document from the time it was created. Okay. Shows the server name, version number. Again, we'll see examples of this. And sometimes the server may be down, but you may have invoked something. It may say, oh, that database is down, but you may have programmed the server to say retry after this. This is the thing that you see that is under maintenance, please try after something. So you can put a message out there. So any request, the response will go with that in the retry after field base. Entity headers again depends, not all of them will be on request or responses. Some of them will be on request, some of them this, but again the same thing. Okay, it tells you what is the type of the language of the body. Okay, what is the length of the content. Okay, what is that type. So this is the language, this is the type. Okay, when does it expire? How long is it valid? When was it last modified? Okay, this location is basically the interesting thing. It's so sometimes you see that you will get redirected to something or something. Okay, so this location is kind of a referral which says that it's not here, but you can get it there, and then the browser can automatically connect you to there, basically. Status codes, again, the huge bunch of status codes, and they're actually, depending on what they start with, okay, they mean different things. So 100s are on the informational, 200s are success. So 200 okay is what you will get most of the time, basically. Okay. Then you have redirections, move permanently, move temporarily, etc., etc. And these are the things that you standard get. This 404 not found, 403 forbidden, okay, and so on. So here is an example. This is your request line. You say get, you give an URL. You see the URL does not contain the complete thing. You can give the complete thing. Okay. But this host field, which is part of the general header, this is a mandatory field. So every request must have the host field in there, even if you give the complete thing here. So if you don't give it, it will just take this one, slash says that you append this to this. So basically you are asking for www.ag.com/index.html, and the protocol that you are going to follow is this. Okay. Here is the browser that is asking for it. Okay. You are willing to accept text.html, but if it is not available, you are willing to accept anything. Okay. And you are willing to accept only English language. So if www.ag.com/index.html is a German website, for example, a German language page, it's not going to give you, you will get a error message back, basically. And you want it only if modified since this. So all these things have exact format specified, the syntax specified and all. You cannot just type are bit things. This n/us, sorry, n-us and all, they're all fixed keywords defined in the RFCs and so on. Okay? And this connection keep alive says, normally when you send a request and the response comes, okay, old days, the connection would be closed. Then for the next request, another connection will be there. This is basically telling the other side that keep alive the connection because I may be sending you more requests and so on. Okay. Response, you will get what is the server responding with, must be the same thing that you send. The status code, usually a status message. Okay. Gives you the date. What is the server? Okay. So it's Apache 2.4.41, let's say. What is the, so these are the entity headers. The green ones are the entity, red ones are the response headers, blue is the request, sorry, general header. It says you have an HTML content and the length of the content is 1846. And then you have a blank line to separate the entity from there, indicating end of headers, and then you will have the HTML file exactly completely out. Okay. Similarly for the put, again same thing. Okay. Note that you can also specify the port. Okay. User agent this. Now you are putting, so you are specifying, the request is specifying what type of content am I sending, what is the length of the content. You are saying after you write it, close the connection. And in cache control, no cache, basically saying you're telling the server not to cache it anywhere or not to give it for caching anywhere. So when the document is given to somebody else, it will go out with no cache in there basically. And again a blank line and the entity body is out there. Response, there can be more fields. I just wanted to show you something simple. So online people, you are with me. I'm going a little fast, but I think these are simple things. And anyway, I will put up the slides just to show you some examples. Is it okay online?
Yes, sir.
Okay. Okay, so I think the only interesting thing to note about this, again, it's a very powerful protocol. I have just shown you very simple things. Okay, you can do many different things. For example, with HTTP 2.0, it's no longer necessarily a text-based protocol. You can actually send binary things. Okay, package multiple things, binary things, and so on and so forth. Okay, but again, mostly it's 1.1 still, as I said. Not everything has moved to 2.0. The only interesting thing to note compared to other protocols that you have seen is a complete text-based protocol. So if you do a Wireshark thing, and if you can connect to an HTTP server, not HTTPS, because then it's all encrypted and so on. Okay, you will actually see this get put. You can see this message format, the headers, and everything out there. Okay, persistent connection is what I just talked about. Old days, the default was that one connection for one request response. So client will open a TCP connection, send a request, response comes back, connection closed. Next request, another connection basically. Okay. So this was what was called non-persistent connection, but lots of time. So old days you only had like a text page or something. So now you have a lot of things with a lot of images, multimedia files ingrained, and so you know that after when this comes back, you are probably going to make more connection to ask for them. So persistent connection is basically one TCP connection made for each request response, and this by the default in 1.1. If you don't want it, you can say that connection : close when you send the request, which means the server will close the connection after sending you the response. Other things that is there, cookies. Okay, you all know about this. The small pieces of data that the server stores. Again, you have fields in there that allows you to do that. So when the server will send you this thing, you'll set basically this set cookie thing in the response. Okay, and you can put whatever pieces of data that you want. It will be stored in some place. Okay, and you can set cookie expiry times. There are many other things with the cookies basically. Okay, so this one will, for example, expire on 30th April, after which it won't be valid. Okay, so if I go to a movie site, and let's say I was browsing and I look for sometimes for Sean Connery's Untouchables. I don't know how many of you have seen the movie. Okay, most likely not. But then so what does the server want to place the server's policy? Of course, But it can send me small pieces of things like this. And the next time I connect to the same site, okay, it can actually send this using this cookie field out there in the request. So now it knows basically that whoever the client is, it has seen these things earlier. So then it can make recommendations of similar movies, etc., and so on, basically. Okay. It can also store my name, for example. And then it can, next time I connect to it, it can say, hello, Aravind Gupta, basically. How it knows it basically, even though I've connected for the first time, because you kind of stored it, because earlier, for some reason, I've typed it in its website and so on. Okay. Finally, HTTPS. It's basically HTTP packaged with TLS on top of it. Earlier, it used to be SSL. SSL is still the name for certificates and so on. Okay, but protocol-wise is deprecated, and it's basically a lot of security things. I will not go into details, but moment you create a connection, the first things that happen is the client will authenticate to the server by providing its regional certificates and so on. Okay. And then if the client is fine, you can have a mutual authentication also, where the server can also authenticate itself to the client. And then you will have a set of commands basically to negotiate the parameters. What cryptographic algorithms are you going to use? You're going to generate keys and so on and so forth. Okay. So that can be one lecture, but I thought it's not worth it right now, again, unless you really have to implement things and so on. So, but basically it's client server authentication using digital certificates, allowed encrypted message exchange, allows negotiating security parameters, what algorithms to use, what hashing algorithm to use, for example, what keys, and so on. But you have maintained interoperability by negotiating capabilities. At the very beginning, you exchange version numbers to say what you can do and what the others can do. So we'll kind of choose the common minimum thing that both the client and the server has. Okay. But then it's the server, so you can set policies in the server to say that the client must have at least this much, or I'm not going to communicate with you. Because you don't want to communicate with an insecure client, for example, basically. So that's all I have to say about HTTP. I was making the slides. There's a lot more materials, but I don't think it's worth looking at it basically in this class. Okay. So online people, do you have any questions as of now? I'll put up the slides. Just know the basics. That's all. But once again, it's everything, the syntax says, gaps, everything is very specific. It's not just you type some text, basically. Okay? But that's a feel that you get only when you actually have to implement things. Now, class sizes have grown, but it was your FTP thing also actually lessened the load. We did some things. Many of them worked, many of them did not work. This your FTP client with somebody else's FTP server and so on. But right now, we cannot debug or anything. But when we do HTTP clients and servers in labs, it's a beautiful thing to watch, because for you to learn for the first time, because we make you connect to a standard HTTP server that we install using your client. We put up documents out there and you download and thing. And this is a standard Apache server or something that we have installed basically. Okay, and vice versa. We will connect from Mozilla or something used to your browser, your server basically. And you should give me at least some plain text documents and all. When you see that happening, you actually feel that you have learned protocol, because interoperability is extremely important. Without interoperability, network is nothing basically. Okay, so any questions from the online people? Yes, no?
No, sir.
No. Okay. So the rest of the class, let me see how many of you are there. Okay, 8 people there and 8 people here. Good enough. So rest of the class, I'm going to do 2 things. Okay. I'm going to start kind of give you an idea about the internet routing architecture. Okay. So you have kind of looked at standard routing and things, but if you think about your standard RIP, OSPF and so on, you understand that you cannot really scale it to the internet level basically. It's impossible to do that. RIP is obviously not. Okay, you need everything within 16 hops. That is not practical. OSPF is also impractical to do that. So that's one thing, what happens. And the other thing, Again, I will give you a kind of a glimpse of when you make a request to like very large things like Facebook, Google, and so on, which for fault tolerance and load balancing purpose actually have multiple data centers. Okay, so how does your request go to the data center? You get one IP, two IP, three IPs or something, but what are those IPs basically and so on. Again, I will warn you at the beginning, you will not understand everything. Okay, but it's more to stir your interest if you're interested. So it's nothing. So syllabus is over, course is finished. This kind of extra things out there. Okay. So these are the things that we have already covered. Protocol layering, basics of IP, basics of routing, route aggregation, okay? Basics of TCP, DNS. DHCP is something that is not very important on an internet scale. It's more for within your organizations, basically, okay? So what does a typical organization, like your IIT Kharagpur's organization will look like, okay? Should have been good to draw, but it's okay. I think it's easy to understand. So you see your wing switches, okay? Your wing switch or floor switches rather. Your floor switches will go to some other switch in your hostels. We'll all, just wires going there, just try to visualize with me. And then from the floor switches, you'll come to something called aggregation switches or distribution switches, which are just switches. These are higher level switches, kind of higher capacity switches. So for some hostels, it's like you have this 3 smaller hostels, all traffic coming to aggregation switch in one bigger hostel. For some bigger hostels, it's just the aggregation switch containing only the traffic from that hostel. Now, all these aggregation switches from there, the uplink port, a fiber will come to CIC. Okay, and the same thing other than hostel, like academic buildings, the same things basically. Okay, so a fiber will come to the CIC. There will be more bigger aggregation switches out there. Okay, and from these aggregation switches, so it will depend on the traffic. So smaller aggregation switches will connect to bigger aggregation switches. If the aggregation switch is already large in a hostel, like take MMM for example, okay, or LBS basically, then it will come to what is called a core switch. So there's different names for it. Edge switches, core switch, aggregation switches, distribution switches, core switches. These are basically, more higher and higher capacity switches. And from the core switch, it'll go through a firewall and through router, and then it'll connect to, we have from Railtel, so Railtel's router. So if you think about an organization taking network connectivity from some ISP, okay, some internet service provider, you can visualize the network till the ISP. Your router finally connecting to the ISP's router. Okay. Now think you have Railtel's router, kind of, it's like a bigger aggregation of all traffic for all Railtel customers. You have the BSNL's router, the bigger aggregation of all traffic from BSNL's customer. Okay. You have Singtel's router, the Singapore Telecoms, aggregation of all things Singapore Telecoms customers. So now just try to visualize with me. You have all these big routers sitting there. Okay. But I can send to somebody who has a BSNL.com address. Okay. So how does physical infrastructure wise, how does my thing, the thing that I send from this IIT Kharagpur will go to somebody in Singapore? Because to do that, Railtel's router has to talk to Singtel's router somewhere. And talking means there has to be a physical connectivity through something, either directly or indirectly and so on. Okay. So that's the question. Where do the packets go once it leaves your organization's final router? Fine, it goes to the ISP's router. But where does it go beyond the ISP's router? Okay. So 2 big questions. How is the physical interconnection between all machines in the world? Okay. And how are packets routed to any machine over the internet? So this is a basic fundamental thing, common sense thing to understand. Eventually, if you want machine A to communicate with machine B, whatever they may be, they have to be connected by some physical path. Okay. And by that may include wireless also, but some physical path basically. Okay. So next, I'll skip some parts of it basically. So here is a broad internet connectivity layout. So end users will buy network connectivity. So we are end users. We buy connectivity from ISPs like Railtel. But these ISPs have different tiers. Okay. Tier 1 ISPs are like the backbones of the internet. Their primary function is not necessarily to give to end customers like IIT Kharagpur or something. Their function is to connect other ISPs, lower level ISPs. Okay. So typically they have large networks of their own, and all tier 1 ISPs are usually, okay, I should put the word usually, connected directly with all other tier 1 ISPs. Okay, because they are the ones that are exchanging kind of, accumulating the data for all the other ISPs sort of. So there's a huge amount of data and you want to do something, you want to do directly basically, rather than going through somebody else and increasing their traffic even more and so on. Okay. And there's a name for it. This is a peering because it's a peer-to-peer connection. This is called settlement-free peering. Okay. So you pre-negotiate what is the traffic I'm going to accept from you and your policies, your payment models, everything you have. Okay. These are all money-making organizations. Okay. But then when the traffic actually comes, you actually just do direct connections out there. Okay. So it provides paths for tier 2 ISPs to other networks. Okay. So again, if you take this example, Railtel here and the Singtel in Singapore, okay, they are not tier 1 ISPs. Okay. But let's say Singtel is connected to a tier 1 ISP X and Railtel is connected to a tier 1 ISP Y. Then X and Y will connect directly. So they are kind of providing the path to the tier 2 ISPs. Now it's not necessary that Railtel need to connect to a tier 1 ISP. I can connect to a tier 2 ISP and then that tier 2 ISP can connect to a tier 1 ISP. Okay. So here are some examples of tier 1 ISPs: AT&T, Spring, that is the orange thing, Deutsche Telekom. Okay. It's not that they don't, I'm not very sure, but it's not that they don't provide service to end customers also, but their primary functionality is to, they also provide connections between ISPs and so on. No, they provide paths for tier 2 ISPs to other networks. Okay, so think of my Singtel, Railtel example as sort of tier 2 ISPs basically, or that X and Y that they connect to other tier 2 ISPs. Tier 2 is peers with other tier 2 ISP direct data transfer or buys transit from tier 1 to reach all networks. Okay, so tier 1s will usually always connect to each other. Tier 2s, if I see a lot of traffic going from Singtel to Railtel, okay, I'll say rather than going through all these things, let me do a direct connection. Both parties has to agree and so on and so forth basically. If not, I will go through another tier 1 ISP basically. Okay. And tier 3 ISPs only buys transit from tier 2 ISPs. Okay. And then this, what is tier 1, what is tier 2 ISP is kind of subjective. Okay. And if you look at different places, it's kind of, there is variations into this thing. Okay. But there is no explicit list mentioned anywhere that this is the tier 1, these are the tier 2, these are the tier 3s and so on. And as I said, a tier 1 can also act a little bit as tier 2 also, can provide, there's nothing to prevent you from doing so. Okay. But this is kind of the broad idea beyond. So this is what it will look like. These are your users, consumers and so on and so forth. Okay. They connect to tier 3 things. These are single homed ISPs. Tier 3 ISPs can be two types. What is a single home? See, this one is connected to only one tier 2 ISP. Okay. This is called a single homed ISP. Okay. Whereas this one is connected to this one as well as this one. These are other tier 2 ISPs. It's kind of broad net. So it's a multi-homed ISP. Okay. So it has, if this connection breaks for some reason, it can actually go through this connection. Okay. And then these tier 2s will all connect to tier 1 network, the tier 1 ISPs, and the tier 1s will be connected directly with each other. Okay. Now you see there is this one thing sitting in the middle. Okay. This is not a great picture. Okay. But this is the one, where are these? So fine, they will connect. Where do they connect basically? Okay, if they have to exchange data. So this point of presence, POP stands for point of presence, okay, is kind of ports in switches basically, where you will connect directly. Okay, but let's say there are 6 ISPs, they want to connect, not directly. They have to connect it someplace. So this someplace is what is called the internet exchange points, IXPs. Okay. So connection between ISPs, ISP routers can directly connect with each other, okay, or they can connect through internet exchange points. These are like giant switches, as simple as that. Okay. So IXPs are this missing link where the ISPs exchange traffic. And just as an example, if you just do a Google search on I think it a huge bunch of them. Some of them are, kind of funded by non-profit funding. Some of them are funded by these operators and so on and so forth. But then you will have policies, and also the second level of routing is all about policies. The first level that you have studied, like the RIP and OSP versus the network and matching, subnet mask, all these things. Not much about policy. The second level of routing is a hierarchical scheme. It's all about policies, basically. Okay. This is, for example, very famous ones, Amsterdam Internet Exchange. Okay, and they have basically, you see this country is this basically. Okay, there are different places also. There's a huge bunch of them. I'll just leave it up to you to look at it later on if you want, basically. So let's get back. But then at the bottom of it, okay, try to visualize. So you have this physical interconnection. Okay, you have to have some routing protocols running anyway. Okay, and we'll see what that kind of the little bit difference between what you have studied and what routing protocol runs there. Okay, it's just that there's a lot of policies there which says who can connect, and then whose data, even if your network allows, I will accept or not. So I can say, fine, Singtel has an agreement with me to send so much traffic per month. Okay, now it is sending to this network. I have the network in my routing table entry, but it has exceeded its thing, so I'm not going to do it. Okay, whereas the routing that you have done so far is all about that. If it matches, send it to the next stop, basically. Okay? So routing in the internet, based on what is called autonomous systems, a collection of networks under a single administrative control. Okay, again, AS numbers are numbers that you have to get from somebody, and it's not easy to get. So IIT Kharagpur cannot get an AS number. Okay. So broadly, the idea is, even though that is not fully true, runs the same routing protocol. Not fully true, but kind of. Okay. Each AS is assigned a unique AS number. There's 90,000 plus allocated AS numbers. Okay, these are 2-3 years old data, but I think you get the idea. Okay. So you have small organizations with AS numbers, very hard to get, but some of those things, as I said at the beginning of the internet, things were plentiful. So things just got allocated basically. Okay. And I said not all active, as you will see if you were interested. So the purpose of this lecture is not for exams, finish your exams, okay? But then, I just want to put some keywords in your head, a general idea in your head. If you're interested, here. If you're not interested, forget about it. So here is what it will look like. These green things are your ASs, okay? You'll have a lot of routers in between, okay? These red ones are called border routers. So the border router will talk with the border route of the ASs. There can be more than one. Okay. So if you think for a second, IIT Kharagpur, if I take routers, I need to worry about all my machines basically. CAS, electrical, etc., lots of entries, lots of subnets and all. But as we have seen in the route aggregation, that the outside world doesn't need to bother about them. It needs only know that this entire chunk has to come to IIT Kharagpur. And then there may be networks inside that I don't want anybody to access for security reasons or whatever. So these borders are kind of my interface with the external world, which says what are the entries I will advertise to the world using those routing protocols. The routing protocols that you studied send out all information. Your distance vector routing will send out the entire routing table. Now this second level routing protocol that I will have will kind of dictate what is the things that I advertise to the external world. I may have a network, but I may not want the external world to know about it. So I will not advertise it to the outside world, so nobody will know about it. Nobody can send a packet to it. And that protocol that runs on top of these things is what is called a BGP. I think I will skip this. These are not important to you. So things that run within an AS are called interior gateway protocols. We did this a little bit, at least the terminologies are introduced in the normal, when we started routing also. So it's routing protocols running within an AS, okay? RIP, OSPF, there are other ones also. And exterior gateway protocols are routing protocols that run between ASs. And BGP is the border gateway protocol is the de facto standard, basically. Okay? So you just try to think with me. So I can have ASs like this, okay? And there will be border routers talking with other these things, okay? So note that for the networks in AS100, for AS200 to know about those networks, okay, has to be only through AS300. So AS300's job, okay, is sort of to advertise any network that it wants from itself to outside, as well as anything that AS100 advertise them to AS300 and 400, sorry, 200 and 400, and vice versa and so on. Okay. Okay. So now just try to get this picture with me. So you have this kind of blobs, which are the ASs. Your RIP OSPF is running within the blobs. And that is exactly how you have studied it. But then there are some routers out there which are running RIP OSPF inside and also running border gateway protocol with the other routers in the other OSs. Are you with me? Picture would have helped, but I think it's still okay to understand. Think of every blob having one special node which is running internally RIP, let's say, with the other ones, but it's also running BGP. But the BGP it is running only with the BGP router of the similar one of the other AS. This is a hierarchical routing, basically. Okay. Is it clear online? Online guys, are you still there?
Yes, sir.
Okay. So now we have to scale to billions of endpoints and have different administrative structures. So far, RIP OSPF was all within one administrative domain. As I said, I don't want that guy's traffic to go through me. Okay. I can have many, arbit policies for who I allow, who I don't allow, what I advertise, what I don't advertise, and so on. So ASs can define policy. Do not carry my traffic over my competitor's network. And of course, you have to specify what is meant by competitors. I don't want to carry AS traffic through my network. Okay. They want to choose their own internal routing protocol, choose their own policy, modify it at, I should not have to ask anybody else to modify my policy. Okay. And least cost is no longer the only performance metric. Okay. It is one of the things. Let us not do this. So question is, if you have to design a protocol like this, okay, so I will just kind of summarize and say, again, what is this protocol that we are talking about? Think of blobs, okay, a set of machines under one administrative domain. Each of them are running either RIP or OSPF or combination, whatever. That is exactly the same as you have studied for routing within their network. Now, some machines in there are special, which are running both the RIP inside with the other machines and running BGP with the other such special machines on the other OSs, according to some interconnection. Everybody need not be interconnected with everybody else. Okay? And they will also have this destination will be again a network prefix. Finally, the destinations are network prefixes. Okay? But I will not advertise everything out there. I will have much less set of things to advertise basically. And I will enforce a lot of policy. So if you want to design such a protocol, that second level routing protocol, would you choose link state or would you choose distance vector? Link state is definitely a bad choice. Because link state requires you to know the entire network topology. Now, okay, as I said, you have 90,000 plus ASs, 100,000 ASs, Arbit connections, okay? And links are not, inside the organization, links are much faster than the other. Chance of loss is higher. So link state is definitely not going to work. Okay? Distance vector may be better, but distance vector doesn't have policy and routing loops can form. Okay? So what BGP does is uses similar ideas, but changes something. Okay? Once again, destinations are still IP prefixes, nothing different. Okay? But then my path I will have as a sequence of this what is called a path vector routing. Okay? I will not just keep the next hop, I'll keep the complete path. If I keep the complete path, if something new comes in, it's easy to check if that something new is already there in the path or not. Okay? With me? So I eliminate routing loops. Okay? So it is general distance vector with 4 crucial differences. I'm no longer picking shortest path routes, okay, by whatever metrics. It selects the best route based on policy, not shortest distance. So that cost thing, I have additional fields basically that apply policy out there. I will not just pick the distance. I will advertise the entire path, as I said. If I advertise the entire path, when I advertise my kind of think of similar thing as distance vector, but then rather than just the next hop, I say for this network prefix, here is the AS number that has to be gone through from me to the prefix. Now if an AS number comes in because of the same counting to infinity or whatever, you can immediately check that AS number occurs there or not, and you don't accept it. So routing loops are trivially solved. Okay? You may not choose an advertise. As I said, the second level is all about policy. Otherwise, it's the same thing. Other than that is sending the entire path, and the path is in terms of AS numbers. The path will not be routers, path will be in AS numbers. Okay? But it's going to be the same thing, basically. And I may aggregate routes, as I said. Again, see, even if you are a tier 1 ISP and then 2 tier 2 ISPs advertise to you, and you see, and you have to advertise it to the outside world. You see that you can aggregate them, you will aggregate them. Because the return path, everything has to go through you anyway. The same route aggregation supernetting that we have done. I will send only one advertisement out of the aggregated prefix. When it comes to me, I will look at which part of the thing it falls to and send it to this ISP or that ISP. Okay. And there's a lot of policies. I will not do this. So this is kind of, kind of a summary thing basically. So you have your data packets in IP forwarding table, the same as earlier. You will have entry, okay. You will have something, a policy adjustment. put the bracket out. Control plane is the routing table. You apply what policies to import, basically whatever is coming in, which ones to accept, choose the best one among them, put the routing table, see what you want to advertise outside. And you can, whatever a policy you can think of, you can apply during that thing basically. But once the routing table is there, it's basically the same routing table that you have seen. Okay? And you have kind of applied the same thing out there. So to summarize, I didn't want to go into any details. I just wanted you to get a picture. My goal is to get a picture beyond, let's say, Kharagpur's router. First step is easy to the ISP's router. So now the question is, if you have these 10 ISPs or so many ISPs all over the world, how are they connected? So physical interconnection, either they can be connected directly if they agree, okay, or through internet exchange points. And there are hundreds of internet exchange points all over the world. And you have agreements who will connect where, etc. So IXPs are the place where ISPs exchange data. Okay. And routing, but then it's finally, that's just the physical interconnection. You still have the routing thing. So how do you route? Again, hierarchical. You kind of break them up into administrative domains, ASs. ASs are, no, you cannot just say I'm an AS. Okay. You have to get AS numbers, you know, you have to configure your routers, everything. Okay. And then inside the AS, it's up to the organization. Do whatever you want to do. But then you kind of have kind of interface routers, so to say, which talk to each other. They can be arbitrarily connected, which are basically saying, again for doing routing table, BGP, but with some differences. Now it's no longer just the least cost path that you choose. Your update thing is not so simple. You can enforce any policy that you want. And it's a path vector protocol, which means you advertise the entire path to eliminate routing protocol, routing loops, basically. Is it clear? Online people? How many people left online? 5. Any questions online?
No, sir.
Then I will quickly go. Let me finish it, okay, rather than taking a break, and do this last part. So the good thing about doing this today is tomorrow there is no class. Okay, we are done, so we will not have a class tomorrow. So this is the last thing that I wanted to give you an idea about. Okay, so you think of any large website, okay, you will have multiple data centers. Facebook's will have multiple data centers spread all over the world. Google has it, okay. Sometimes you have your own data center or you host it on some clouds here and there and so on. So question is, how do you route a request? Let's say I make a request standing here, www.google.com. How does it go to one particular data center of Google, basically? Okay. Now, a disclaimer before I say, this is not to explain exactly what Google and Yahoo does, but I think you will believe me that this is going to work. And this is the, in essence, what happens, basically. Okay. So ignore the second bullet. I had this lecture long ago, 2-3 years ago, as part of a course on data center networks I was giving somewhere else. Okay. Okay. First of all, first thing you notice, think with me, that if you start with x.com, DNS has to come. There is no option. Okay. So DNS will look up x.com to get the IP to connect to. Okay. If you do a google.com, this was done long ago. Okay. But this MX Toolbox is a very famous thing where, just, you can ask for any type of DNS records and so on. You get one IP. You see is Google's AS number, 15169. Okay. But Google is not one IP. Obviously not, cannot be. Okay. And these are, you see, reported by ns1.google.com. So it's an authoritative answer, basically. If I do yahoo.com, I get lot more things. There are more things below this. Okay. But still it's going to be much less than you finish, then you let me talk. Very disturbing. When you talk, when I'm talking. Okay. Ask me now, and everybody gets to know. Okay. And you see Yahoo's ACE number also out here. So what happens? Google gives only one IP address. Yahoo gave 6. Okay, obviously Google doesn't have one server or something. Okay. So what I will try to do, starting from this IP address, is the first step. What happens? Okay. So here's the broad scenario that matches Google, Facebook, Amazon, all those people. A company operates multiple data centers, geographically spread all over the world. Request for services comes from all over the world. Now the company would like to direct this request to the quote unquote appropriate DC. What is your goal? You want to load balance across the DCs. Okay. You don't want to send to something that is down. Okay. You want to send to something that is close by, because otherwise the network latency is too much. Okay. And it's fascinating. I will not go into that, okay, because that's not part of this course. It's fascinating how much thing happens when you type something in Google, a search, and it comes back to in a jiffy. It's unbelievable how many things are happening and how many devices is going through. Okay. So you want all these things to happen. What are some of the technologies at play that we look at today? DNS load balancing, then there's something called GSLB. These are not complementary things. Okay, these we'll see basically. Load balancers, something called virtual IP and routing. Just one slide on that. So one possibility is that DNS can do load balance, and DNS does do load balancing. You can actually put more than one IP for a particular name in DNS, and DNS will typically give it to you in round robin fashion. You can put multiple A records or CNAME records. Okay, CNAME is just an alias. Okay, so it can give them all out on query. Typically, it does in round robin fashion. Okay, but then, oh sorry, DNS gives everything together. Client picks it up typically in round robin fashion. But then, first of all, there is no standardization as to in what order the client will pick. Sometimes choose the first one, sometimes choose the round robin, but then round robin is within what? Only for the requests that are in the client. Okay, try to think with me a little bit here. Okay, so a DC is getting 1 million requests. You are making only 100 of them. So my client sitting here, so DC gives me all 4, the DNS gives me all 4 IP addresses. But my client, okay, can only get this out of this 100 thing. Okay, the rest of the 1 million minus 100 people, even if they do something, okay, they may all put the same thing. Okay, so it's not round robin even within the large set of things out there. So no standard definition, first of all, so you cannot have guarantee. So DNS servers typically will send the list in a cyclic order, so that even if you pick the first one, so you do all these kind of hacks out there. Works for a little bit of load balancing, but at that scale, where you have like millions and millions of requests sitting aside, is no good, basically. But good to know that DNS can do load balancing. So if you have some servers and you have not such a great thing, but you still want to load balance a little bit between 2 servers and so on, you can actually do it. Okay. So con is obvious. Now, you see, we have to start with DNS. Okay, let's try to design this. Okay, you have to start with DNS, but at the same time, just think of this very simple scenario. I have 2 sites, okay, and the first client I want to send to the first site, the second client I want to send to the second site, always. Just a simple round robin, but among those 1 million requests. Okay, which means I have to make DNS do 2 things. Okay, I have to kind of make my own DNS. So my problem was that the DNS server is a simple static policy. I have configured something static, 4 servers. The DNS said, I will give them in a static way, cyclic order. That's it. Hoping that the other side will pick the first one, all of them, and then therefore it will be round robin. Okay. GSLV is something like an intelligent DNS. So other than the normal zone file lookup, what it will do is will keep track of which servers are actually up, current load on the servers, geographical origin of the request. I can map from the IP, okay, and access any other information relative. So when a request comes, it's sort of I will look at which server has the highest lowest load, and I will send that server's IP out. Okay. So before sending the lookup result, GSLB server can apply any policy. Okay. But that means that it has to continuously get updated with those information. But that's the idea. Okay. So where will this GSLB server be? First of all, it cannot be a standard DNS server that you download and install basically. Okay. You don't have the Linux standard Linux DNS server. I want my things installed in there basically. Okay. So you can integrate with the DNS code, but nobody does that. Because that's not modular, you cannot change it, it's inflexible. So you can implement it as a proxy. Meaning what? That the server IP, okay, given as DNS name server IP. So now think the name server that I advertise, that Google advertises, it's not really a normal name server. It's a special server that Google puts. So your request, but you think it's the DNS server, but that's what Google has kind of advertised a DNS server. So your requests hit that server. That server, first of all, now calls the DNS server of Google, which is hidden from you, gets those 10 IPs. And now sees, applies a policy on them based on the load that it is measuring and so on and so forth. Say, oh, 4th IP is good now. Give out the 4th IP to the other one. Works, right? Now, you can have your own such intelligent server, but many things like Cloudflare and all provide you such services. So you can host your server in the cloud rather than your own server. So you have your DNS server, okay, but you have your GSLB server sitting in the cloud with all this facility. Okay, that's just a matter of where do you want to host, whether it's, so the problem with having the GSLB server in your organization is then that GSLB server gets loaded. Okay, you want to basically get to the DC, but kind of spread the load on the DC. But then if you put the GSLB server in one of your DCs, then that DC anyway gets loaded because everything is sitting there. So you put somewhere else. You can put it on ISP. You can put it on standard things like I said, Cloudflare and all. They give you these services. GSLB goes by different names. Okay. But you will hit that. That will first do the DNS lookup to find out what IPs are possible. And then, but it also has, you have put your code there to monitor your IPs, put whatever policy, applies a policy, gives you back that thing. And one of the simplest policies can be, as I said, you got the request IP. There's a standard way of finding out for the reverse lookup that this IP belongs to which region. Okay. So one simple policy can be get the IP DC which is closest to that region. With me? But then GSLB is not enough for our scenarios. Okay. So go step by step. We start with DNS load balancing, good for very small load balancing, not good for DC level load balancing. So GSLB. But then what is GSLB doing first? It is getting a set of IPs from the DNS. How many IPs can we advertise? 10, 20, 30, 40, 50. Okay. But then you understand even 50 servers will not be enough to manage like Google, Facebook kind of load basically. So what you get basically as those IPs are not IPs of servers which are actually doing your lookup. Okay. You are basically getting a load balancer IP. So now it's a hierarchical. You hit GSLB, GSLB goes to DNS, gets 10 things, 10 load balancer. Because GSLB cannot maintain also, not just you cannot advertise, you have 1,000 servers. How is GSLB going to measure the load on 1,000 servers? By the time you measure the load on the 1,000 server, the first server load may have changed already. Right? So you basically again break it up, and this is standard design technique. When you want to scale, you make things hierarchical. You cannot scale flat. Okay. So you are hitting a load balancer. You are kind of looking at the aggregate load of that load balancer. And then sitting behind the load balancer is basically your servers. And you can, again, if you have lots of servers, you can have hierarchy of load balancers also. Too much hierarchy is not good. That increases the network latency and all, basically. Okay. So you hit load balancers. And they are interesting devices. They have to be very, very fast. Okay. And there are standard companies like F5, Citrix, Radware, Fortinet who specialize in making load balancers, basically. And you can put again many policies out there and so on. Okay. So this kind of a feasible architecture. This kind of my summary slide. Virtual IP I'll talk in one slide on. So each DC has a small set of N load balancers. All servers in the DC are partitioned into N clusters with all servers in each cluster connected to one load balancer. So that load balancer is in charge of measuring the load on only that cluster of servers. So you have to want to keep things manageable. Every load balancer monitors and collects information on N servers. Each load balancer makes a summary load information which is fed to the GSLB server. What? You can, okay, but usually you can, theoretically. Well, again, if you have to scale, it has to be. You cannot have two reasons for not having one GSLB server or one server for anything, basically. Okay, one is scale. If you have a lot of load, other is how critical your service. If one fails, what happens? But never forget in design cost. If my server in CSE fails, I can keep it down for, it doesn't matter if I keep it down for 2 days. Well, people are inconvenienced, but nobody loses money or nothing happens. But bank server cannot be like that. Okay. So the IP is against the service name in the DNS server, the IPs of this load balancer. GSLB monitors these load balancers. Client send request, GSLB taps, sends to DNS for name lookup. DNS gives IPs of load balancers. GSLB applies policy on them, sends one of the load balancer to this. Client sends a request to load balancer, then load balancer applies its own policy to direct the request to downstream servers, basically. Lots of details underneath because we are talking at a very high level. These are the parts that I'm completely skipping because you wanted to make a TCP connection to something and you have now got lots of devices in the middle. Okay, what are the TCP connections going to be, basically? But these are good things for you to design if you are interested. And as I said, can extend to multiple levels of load balancers. Finally, this is something that I will just mention. Other than this, load balancers, you have something called a virtual IP. Okay, so virtual IP is not assigned to any physical network interface, but in your router, a virtual IP. So kind of your destination will be a virtual IP, and in the router, it will be matched with multiple physical IPs. Basically, physical IPs mean IPs that are assigned to physical machines. So up to the router is going to be one IP that is advertised to the outside world. So you think that that's your X load balancer or whatever server or whatever. When it hits the router kind of sees, oh, it's actually a virtual one, and I have 4 IPs backing it, 4 machines backing it. Then the router is going to send it to, as per its policy, usually round robin. So that's another way to load balance, basically. Okay. So to summarize, remember that everything has to start with DNS. Okay, because we have a name, finally everything is with respect to connection. Okay, so natural design processes, can I make the DNS more intelligent? Okay, so that's where GSLV comes in. There are different names for it, different things. Nowadays devices pack too many things in one thing and so on. Okay, but broadly that's the idea. One place where you are going to hit the policies basically. And then, but again, if you have, depends on your scale. Those 10 IPs that the DNS gave you could be your server IPs also. Okay, or you had a load balancer, then you, depending on your scale, you have another load balancer and so on. But then you don't want to do too much scale. Okay? Because as I said, you'll be surprised like how much time you actually have for actually doing the processing. Okay? And there's very interesting things happen because you did congestion control. So congestion control is a very interesting topic in data centers. So last try, okay? So you think that your request comes in. Now you want to search. You want to search in millions of documents, right? So you break up the search to do in parallel. So give it to 1,000 servers in parallel to do the search. Okay, so it's like a tree structure with 1,000 branches. Can be hierarchical. Whenever you have scale, think hierarchy. Okay. Okay. So all these thousands went fine. You submitted the thing. Each of them found some time, some results. When they tried to send it, while going out was easy. Because you just did very small thing. You have some small phrase or something that you would say. Okay, that small thing went to everybody. Now everybody is sending you 50, 100 documents on which you will do something, do a rank and so on. Okay, now all of them are coming towards you at the same time. Now going out there was no congestion, coming back there's huge congestion. And the amount of time that you have is so small that you cannot say let them randomly choose between this large time and so on. So very interesting problems when you think about it. Anyway, there's a lot of, I think, online attendance has dropped to what now? Anybody left? Yes, those 5 stalwarts are still left. Okay. And offline people are all sleepy for your information. So I'll end here. I just wanted to give you an idea. And not for exams. After the exams, if you are interested, you can look up, contact me and so on. So course is over other than the exam. Any questions from online? Any questions, anything from the online people? You can hear me, right?
Yes, sir.
Yeah, you hardly moved today. Okay, in that case, we'll close the class. Thank you. So, long, strange semester. Hopefully, this will be the last strange semester. But good that I got to talk in front of few people at least, basically. That feels good. So, okay. If you have any questions, you can always send me. And other than that, it's just the exam. Chalo.